Hey there, welcome to the channel. So today I want to discuss green energy and why it doesn't work. Okay, so everyone's going to hate me for this one, I'm sure, but I want to take a minute and I was looking into green energy and um, I'm an engineer and I come at it from more of a scientific point of view, these things. And there's a lot of focus on green energy and things like the Green Energy New Deal. And there's this belief that we can basically convert our economy from a carbon based economy where we use fossil fuels to provide our energy, which of course provides everything, including our fuel, and just runs the entire economy, that we can convert that to a carbon free or a carbon neutral economy. And my understanding was looking at it is that due to the energy density, that this is really a very unrealistic thing to expect that we can do. But in spite of that, people on the green side of things and the social justice warriors kind of push and push for this narrative. So what I did is I said, well, let me look into it. Maybe they're onto something. Maybe there's something I don't understand. Okay, so first of all, trying to understand what energy density is. And so I found this website, University of Calgary, which is in Canada. And energy density is the amount of energy that can be stored in a given system, substance, or region of space. Now, energy can be measured in two different ways, by volume or per mass. And this is what I found to be kind of a challenging kind of thing because different charts have different things and you really want to compare the same thing. So you want to have a chart that's comparing the energy per mass or per volume. Now, in this particular chart, so here we have a chart here comparing the energy density of different fuels. Now here it's important to understand this is megajoules per kilogram. So kilograms are mass. So this has to do with mass. And this makes a lot of sense from the perspective that, this is wood. This is a chunk of wood. This size wood has 16 megajoules per kilogram. So it's really low. And then coal's a little higher, ethanol, bio, crude oil, diesel, gasoline. And you see yourself in the crude oil, diesel, gasoline, you're at, 44 to 46 mega, meaning million joules per kilogram. And now a joule is pretty small, so that's not a great thing. But compared to like wood, it's much better. There's a much higher energy density. And then you go to natural gas and it's 55, it's much higher. Now here they have a chart and they claim that uranium-235 is 3.9 million. So what you see here is you see that, some indication of why there's been kind of a conversion in industries away from coal. This is one of the indications for that, is away from coal to natural gas. One of the reasons is that, it has a higher density, but of course there's more to it than that. It also cleans burner, et cetera, in terms of per unit emitting carbon. So the point is, and then this number here on the uranium is a very, very high number. So this really says that, uranium is the key to all this. But let's look at some more. So I found this other paper. In this paper here is making another comparison. And this is from Taylor and Francis Group, LLC, Bradley Lawton here. And he has this chart over here. And what he's comparing here, now he's comparing it energy density in its joules. So it's energy per cubic meter. So now it's per volume. So and we have a comparison of solar, geothermal, wind, 10 mile per hour, blah, 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 tidal, human, oil, gas, et cetera, different cases, natural gas. So now if you look at it in terms of per volume, and this of course is an important thing, so your solar is this minuscule. It's almost just not there. It's 0.000015 joules per cubic meter. So it's just incredibly small. And then a little better for geothermal, wind, tidal, et cetera. But there's your good old oil is at 45 billion, 45 times 10 to the 9, 45 billion joules per cubic meter in the 10. So the point is the relative comparison. Now, does this make any sense? Well, it does. If you take a car, we can take a car, put 10 gallons of gas in the thing, and you can drive that car. You can put a gallon of gas in a car and get 30, 40 miles per gallon on that thing. how many miles can you go with a solar panel? You can't even move a car. You can only move those really very experimental cars that are basically thin pieces of paper. So this is the problem. This is the problem with getting off the carbon economy. You have these newer solar, wind that have energy density that is so poor, it's so low compared to what we're currently using, which is gasoline and oil, that it's very difficult to move to that. Now let's look at another aspect. Another aspect is looking at this other website here from the Office of Nuclear Energy, and I believe this could be a US government site. But one of the other things is that the capacity factor. See, the nuclear is actually very reliable. It basically, what this is saying, that the nuclear plant has to come is up 93.5% of the time. That other 6.5% of the time, you got to take the plant down. You're doing refueling, it's offline. Natural gas plants are only up 60% of the time, coal 50%, hydro 40%. And it's not only just to refueling, et cetera. It's about, like, look, if the wind isn't blowing, you're not going to get any. If the sun isn't out, you're not going to get any power. If the hydro power plant, if there isn't enough water, you can't run the turbines, et cetera. So you can see how poor this is. And the implication of this is that for solar, so if you're going to take a plant, given at any size, a nuclear plant, and a 50 gigawatt plant, for example. Well, if you want the same 50 gigawatt and you want it in solar, because solar is only running 25% of the time, you need 4 more plants. So basically you need to build 200 gigawatts of solar power just to replace that. And it still doesn't completely work, right? It still doesn't completely work because you're not, at night, you're just not going to get anything from the solar, even though you do have the new storage technologies that improves it, but still it's not as good. So now I wanted to look at another chart here. This is a better one here. This is a more formal paper, and this is Energy Policy, Spatial Extent of Renewable, Non-Renewable Power Generation, a review meta-analysis. So by this John V. Zalk guy. So this, and this is on ScienceDirect.com. So this is a much more academic paper, and this is basically a review in meta-analysis. So what this means is they didn't write a paper. This paper is about other papers. So they've gone through all the literature, they've read all these other papers or all the analysis about what the power density is. And what's good about this guy here is it's very detailed analysis here. And it's actually, there's some surprising results in here. But what they are doing is, they're actually comparing fossil fuels like natural gas and then nuclear and then oil, coal, solar, geothermal, wind. They're comparing them all to each other in power density, watts per meter squared. So this is really good because we can get a really good comparison. So if we zoom in on that chart, you can see something here. This is actually surprising. So this is something that I learned myself. Natural gas has a higher energy density than nuclear. Now, how could that be? And the actual natural gas itself doesn't have a higher energy density than a pellet of nuclear fuel. But the issue is they're trying to, I believe what's going on here when I read through this is they're going through all the calculations to figure out, like, okay, but you're talking about power density per meter squared to build a real plant. So this is to build a real nuclear power plant, a real natural gas plant, oil plant, coal, solar, et cetera. But here's the real problem for renewables. No matter how you cut it, when you look at your renewables, they're all just really, really low. So, wind, geothermal, solar, these values. So N is the number of calculations they found in the papers in median. So we could just use the medium. So here, solar is 6.6 energy density. So it's 6.6 watts per meter squared. 2.24 for geothermal, wind is 1.84. Well, look at a nuclear. Nuclear is 240, right? Natural gas is 482. So all of these guys are at least an order of magnitude more. Some of them too, so this is like it's 20 times solar. So this is the fundamental problem. And this is why renewable energies, like in the Green New Deals, as they're proposed now, will not work. One of the things to note here is that your coal, oil, nuclear, natural, the only ones here. So basically your carbon ones are going to be your nat gas, oil, and coal. Now, these guys are emitting carbon. So these are the ones that are bad. These are the ones due to climate change and global warming that you want to get rid of, right? Because we burn these and they create carbon. This group down here, not so much. In the biomass, I'm not sure about that, but it's very small, so I'm not going to really address it here. So, but these are more carbon neutral. They're not producing carbon all the time to produce energy. So this is really good. Low carbon output, high carbon output out here. But the question is, the energy density is so low that these are very unworkable. So, for you to generate any kind of power with a solar plant, you need massive amounts of space just to make an equivalent plant, equivalent natural gas plant. It's 482 compared to that. So it's a huge multiplier. Natural gas is so much more efficient from the power density, from the number of amount of power per meter squared that can be generated. So your only solution then is what? Nuclear. It's your only one that when the thing is up and running and it's operating, it's not producing carbon. It's producing very little carbon. I mean, there is some for sure, but this is going to be your gold, holy grail option here. So that's the only option. So if you were like a greenie and you're really concerned about climate change, this is the target power. Now, this also, it's interesting. Some groups are starting to declare nuclear as a green energy, which is really funny because, I grew up in the 70s and we had the no nukes concerts and all that and all those protests, and for rightfully so, because we had the 3 Mile Island, which was nothing in the scheme of things compared to Chernobyl and compared to Fukushima. And so that's kind of the issue. So you have to understand that this is the physics of the world. This is what it is. So you can't just wish it away. You can't just build tons of solar plants, wind plants, and be happy and think that you're doing something when you're really not, because you're not replacing all this power. You can't replace all this power. You're so far behind the curve in the basic physics of this stuff that it's just not going to work. You cannot scale it. And there's an interesting TEDx talk from a guy who helped build one of these solar plants out in California, because we have these huge deserts. They're not far from where I live. And he's like, we're relocating turtles. And he kind of just saw the error in his ways. Like, he's like, this is just an environmental disaster, this solar plant, because it's like, hey, we got to like dislocate all these turtles. I mean, it's the desert, but there's all kinds of stuff living in the desert, right? And, he's just like realizing this isn't working. Now, the counter with nuclear is nuclear is a disaster. We got Fukushima, which multiple reactors, total freaking meltdown, massive amounts of water just that is radiated. We have all these tanks of storage of radioactive water, which is still a disaster in progress. It's still a disaster in progress because, when they get the next big quake or the next tsunami, which they will, because they are Japan, those things are going to crack open and dump more radiation into the water. It's just a disaster. So I get it. I'm not a big fan of nuclear, but if you want to reduce the carbon that we put in the atmosphere, then nuclear is your only option. Okay, so now we have to look for real solutions. We have two problems. Problem one is we are putting in carbon into the atmosphere, right? Second problem is we've already put a bunch of carbon into the atmosphere. How do we get this carbon out? How do we get back to some more neutral level? And, that's something someone can determine. Is it pre-industrial revolution? I don't know, but it's probably something less than it is now. Here's what I think is the answer: molten salt reactors. Now, these are a class of fission reactor, and basically the fuel is a mixture of the coolant and fuel is a mixture of a molten salt mixture. And what's interesting is apparently these reactors, the US had one of these in the 50s and 60s and did a bunch of experiments and stuff. And China, of course, who is being smart on this one? China is apparently getting ready to start one of theirs. And these are the good ones, the thorium molten salt reactor. These are really good because what happens is these are considered safer because they operate with fuel that's already in a molten state. In event of emergency, the fuel mixture is designed to drain from the core to a containment vessel where it will solidify in fuel drain tanks. So what happens is this prevents uncontrolled nuclear meltdown and associated hydrogen explosions. So there's several things here. First of all, it's already in a molten state. The second thing is this also has to do with like the cooling. It's not, you have to understand like what happened at Fukushima. Part of what happened was you had expended rods that were so hot that they needed to have water continue to circulate around them. When the pumps go, the water boils off, the rods start irradiating all this nuclear stuff, and then you have all these chemical reactions going on. You got hydrogen release and explosions, and it's a disaster. And so here's really what the solution is. Now, what I would say is this: if you really care about the environment and you care about global warming, this is the kind of thing that we have to start moving to, because you got to understand. You can get mad, you can get angry about it, but the simple fact of the matter is that the energy density that you're looking at here is just insufficient in these renewables. It's insufficient energy density to make them practical to replace the energy needs that we have at this point. Secondly, that would help with the problem of putting the carbon in the atmosphere, right? Switching over to MSR type of reactors, going towards that would help the problem that's getting worse by putting carbon into the atmosphere, right? And it would ripple, because right now you have all these electric cars and everything, and you have solar panels, energy storage now at houses, electric cars. A lot of those electric cars are still running on what? Natural gas, right? They're not running on a renewable energy. And California has this thing, we're going to by 2030 or whatever it is, we're going to be all on renewable energy, and it's just not going to happen. I mean, I think that in California, if it happens, well, they'll cause just an economic disaster, because I mean, I can already see like what they're sending out with the energy bills, that they're trying to go this direction, but it's a disaster, because it's like, look, you can't run any kind of a company here. You can't do anything with that because it's just too constraining, and they won't get it right. Like, if you want to go to renewables, you have to build the renewables first. You have to get that well entrenched before you start shutting down your fossil fuels. And that's not what they're doing. Okay, so the second aspect of this, they have this X Prize going on, and what's going on is they're looking for, like Elon Musk and this other guy, looking for proposals for removing carbon from the atmosphere. So it's carbon removal, right? So this is the other problem. The problem is that we've already put all this carbon in. It's already too much. I mean, it's already beyond that 2-degree threshold. I mean, it's already happened. It's a feat accomplished. It's not something that we can change at this point. And this is another problem. We have to be a little bit of a realist. It's like, sure, ideally it would be better not to have put the carbon there, but it's there. What are you going to do about it? You know, are you going to do something about it, or just cry about it? Well, here's the key. The key is that some of these technologies may, in fact, be very energy intensive. So you can't find yourself in a situation where you're burning natural gas and firing up natural gas plants, you know, to run carbon capture. You can't do that if you have natural gas putting more carbon in, even if it's like, even if you have a net negative carbon footprint, right? So even if you generated whatever 100 million tons of natural, let's say you put 100 million tons in and get 200 million tons out. Okay, so you got a net 100 million tons removed. Okay, that's better. That's fine, but that's still not really good enough for the scale of what you're dealing with. It's not, and hence you have to go with you have to go with the salt reactors, because then if you're putting zero in and you have a process that is now maybe more energy intensive, first of all, if you have enough of these reactors, you can make the cost of the energy very low, which will make the cost of the carbon capture much lower than it is now. So it's twofold, and there's a synergy there. The synergy is that you develop these new reactors, they're much safer, they reduce the carbon footprint, they reduce the carbon going into the atmosphere, and at the same time, you now have a potential energy source to help you power carbon capture. All right. Well, leave me hateful comments in the comments below. Talk to you later.